Thanks so much, Andrew, for the kind introduction, and thanks everyone for attending. So the work, as Andrew mentioned, I divide my time between the University of Washington, where I'm a professor, and Google. And the work that I'm going to be talking about today is from the University of Washington. So that's why Google's in parentheses here. All right, so there's a science fiction author, Bob Shaw, who in the 1960s came up with a really intriguing idea that I want to talk about today and focus on for this talk. And it's something called slow glass. And the idea is that it's a pane of glass where light slows down when it passes through the glass. So when a light ray enters this pane of glass, the speed of light slows down dramatically before it comes out on the other side. And it slows down not just a little bit, not just nanoseconds or milliseconds or something like that, but years. So it may take years for light coming from one side of the glass to come through and emit on the other side of the glass. Okay, so of course it's science fiction, but it's pretty interesting. So what does this look like from the other side of the glass if you're looking through it? So if you installed a piece of this slow glass at a tourist site like this, what you would see would be something like what's depicted in this mock. And the idea is that you would see, when you look through this pane of glass, you would see people, 100 years ago, for example, if it's a 100-year slow glass. This would be superimposed in the scene as it is today. And not only would it be just a photo like what's depicted here, but you would see people moving through the scene as they did at that moment 100 years ago. And it wouldn't just be, like a video, but it would be kind of immersive in 3D. It'd really be like looking through a pane of glass as you get the full parallax effects as you move your head from left to right. And of course, there'd be audio, and it wouldn't be just black and white like this picture is showing you. It would be full color probably. All right, so that's the idea. So another example, if I installed a piece of this slow glass in the White House in Washington, D.C., 150 years ago, and it was a 150-year-old piece of slow glass, meaning light takes 150 years to pass through, what you would see today, if you look through that pane of glass, would be Abraham Lincoln just sitting, working on the other side in real time. It'd be just like you were looking at Abraham Lincoln live. But of course, the world as you're seeing occurred 150 years ago. So that would be kind of amazing. So the question is this possible? And I'm not a physicist or a material scientist, so I can't say for sure. It seems a little bit far-fetched to do this optically. But you could imagine doing something like this using digital technology to simulate this effect. And that's what I want to get into now, to really try to take this apart and figure out whether you could achieve slow glass. So let's look at individual components of what would be necessary to make this possible. So one thing you would need is you need to be able to simulate a window where something is displayed on the other side of that window. And that's kind of hard actually. So you need to be able to, normal screens are 2D. This has to be like a light field display, right? So you need a lot of cameras probably to capture it. So there have been attempts like this Litro camera from a few years ago, and they had dozens of cameras capturing the scene over sort of a wide field of view and physical space. And this essentially is something that you could use to capture a window of light rays. And so this is a piece of technology which could be relevant for this problem. And it's sort of a demonstration that it is possible to do it, although extremely expensive and hard to do. Okay, but even this doesn't capture every single viewpoint you would need to get a full parallax effect. So you would need view interpolation algorithms to generate the continuum of in-between views. And of course, this is an area that there's been a lot of progress by many people in the research community over the last several years, to the point where, you know, it seems quite likely that there'll be kind of excellent photographic quality view interpolation algorithms that could handle this problem a few years from now, that will have almost no artifacts, or it'll just fool the viewer into feeling that they're looking through a window. So this seems doable, hard, a lot of cameras, but combined with view interpolation, probably it could work. All right, so now you need a display technology to be able to show the scene on the other side. Okay, and you need this display technology which is capable of giving parallax effects as you move your head back and forth. And so effectively you need a light field display. Now, hard, but also this is a problem where there's been some progress as well in the display technology. This is an example some of you may have seen from a company called Looking Glass, and they have a basically volumetric display technology. It looks like a thick piece of glass, but it can render digital objects or 3D reconstructed objects, which appear to be inside the volume of the glass. And this is glass is free. You don't need to be wearing a head-mounted display to see it. The quality is pretty good. And in this case, the object is inside. It appears to be inside the glass as opposed to on the other side of the window. But you know, you could use very similar technologies to achieve the latter effect as well. Okay, so this is promising. Looks like we have another ingredient of our slow glass kind of coming together. Okay, but suppose we're able to do all of this stuff, then you get to the really hard problems. So for example, there's a lot of data, right? So you saw those cameras. Wikipedia has a nice calculation, which is that if you take an 8K video camera and you record for 100 years, and suppose it's uncompressed, that requires amount of data on the order of exabytes. So to give you a sense of exabytes, that's really kind of a data center. So you need a data center to store the kind of data you would need to pull this off. And that's just one video camera. If you had 64 video cameras or an array or whatever, you might need multiple data centers to really capture all of that data. Okay, so that's a challenge. But I think even harder than that, even harder than requiring a data center, is coming up with a device which can record continuously for more than 100, or on the order of 100 years, right? So imagine just having a piece of technology that you place in the field and it just works for 100 years continuously and is robust enough to not break down and so forth. There's nothing out there now that really lasts that long, at least in the technology sphere. So this is incredibly, incredibly hard and maybe impossible. And even if you were able to do that, what format would you record the video in a way that could be played or decoded 100 years from now? Formats typically only last few years or decades. So anyway, okay, so and believe it or not, if you're able to solve all of these really hard problems, then comes the hardest problem of all, which is we need a time machine. So how can we capture Abraham Lincoln? We really need to go back in time to be able to pull this off. Okay, so this is all pretty challenging. Now, wouldn't it be great if some folks 100 years ago were kind enough to just record light field video for us that we could use right now? Wouldn't it be great if there were camera arrays 100 some odd years ago? And this turns out is not actually a light field camera. It's just a really big camera. Well, turns out they did. Turns out there are camera arrays from 100 years ago, and lots of them. They look like this. So this is camera array from the last century. Has two cameras, so it's not a big array, but it's enough to be interesting. So stereo cameras were very popular around the turn of the century. And there's tons of imagery, and they were used to capture. So Abraham Lincoln was, in fact, captured by a camera array. And here's one of multiple photos that still exist, stereo pairs of Abraham Lincoln. And this is pretty cool. So from this image, you know, we have enough that we could actually measure the shape of Abraham Lincoln's body, for example. Only up to a scale, because we don't know the camera baseline and so forth, caveats, but that's pretty interesting. And in fact, many figures from history have been captured in stereo. So this is Mark Twain, famous author. And why did people do this? Well, it turns out you can create really compelling visualizations by putting one of these stereo cards in a stereo viewer, and then watch the scene in stereo. Gives you a really compelling effect. So this is the antique stereo viewer. Stereo viewers, this was really popular before TV. Kind of, you know, this photo is from 1923, showing kids going to libraries. Remember libraries? And you used to be able to go to a library and check out stereo cards and viewers and look at stuff in 3D, and this is pretty popular. And this is, in fact, a meta stereo card, which is kind of cool, meta stereograph. So it's a stereograph of people looking at stereographs, which I found interesting. So stereo viewing has been popular, you know, through a lot of the 1900s. So many of you may remember, at least those of you who are close to my age may remember the Viewmaster, which, you know, I had as a kid, let you see stereo views and so forth. And so you can get this stuff at any antique store. So they'll have lots of stereo cards and stereo viewers. And in the back of my mind, I've been interested in doing something with this imagery for a long time. And it's one of these kind of back burner projects that I always wanted to come back to at some point. But it was really hard to really use this imagery because you know, just scanning in the cards is hard. The cards are actually curved intentionally, so they fit better into the viewer, and scanning them would kind of be a pain. So something really interesting happened in the last few years, which made this kind of data a lot more accessible. And let me just give you some context on that. Back in the 1800s, there were lots of photographers who would capture this kind of content, and lots of companies which would produce and distribute the stereo views. But over a sequence of events, the companies kind of eventually all got bought out and merged into a single company called Keystone View. And by 1935, they had 2 million stereoscopic views. This is kind of incredible. In 1935, just imagine having 2 million photographs at all. So this is quite a collection. And over the years, eventually Keystone went out of business. And the last owner of the material of all the Keystone data donated it to the University of California, Riverside Museum of Photography in 1978. And this is huge. So now it's essentially owned by this public entity. And Keystone and University of California, Riverside has now started putting this data, scanning the stereo views in and putting them online. So they now have tens of thousands of stereographs online. And this is great because it means we can start doing something with all this data. So here's what one of these stereographs looks like. This is Thomas Edison in his laboratory. And so it's pretty good quality. One of the things you may notice if you look closely is that there's a bit of vertical offset between the left and the right image. And this just has to do with the way that these stereographs are constructed. Basically, when they're imaged, the images are transposed left and right. And so to create the stereograph, you actually have to cut the negative and reassemble it. And in this process, often there's offsets like this that occur. There's a number of other things that can go wrong. Underexposed, overexposed. Sometimes in the scanning process, there are mistakes, like only one of the two stereo cards is scanned, or maybe the images are flipped, like in the bottom right. So we had to do a bunch of cleanup to really get this data in a form which is usable for computer vision, computer graphics community. But we did, and I want to show you some results of the data. So here's just a small sampling of the tens of thousands of stereographs, just one of the two images. And then on the right, you can see the disparity or depth maps that we've estimated from these stereographs. And so we're processing all these images, and we're just about to put them online. So go to this, if you go to this website, keystonedepth.cs.washington.edu. This is where we're going to put all this data. And if you go there now, you can fill out a little, enter your email address, and we'll send you email as soon as it's ready, which hopefully will be in a few weeks. So this will have the photos themselves rectified, so just horizontal parallax, calibration data, metadata, and so forth. So hopefully it's a great resource for the community. Okay, so let me just very quickly take you through what this data looks like. It spans like a number of years, ranging from the end of the 1800s through mid 1900s. Here are just a few of the keywords. So there's descriptive text that goes along with all the data, and the size of these keywords are proportional to how many images have those keywords. So a lot of different things covering a cross section of people's, places, and things. Just a few examples. So a bunch of images of presidents. So I think most of these are of Theodore Roosevelt, but there's a number of other presidents during this period. 500 images of presidents. And then, things ranging from cars, antique cars, to archaeological sites, to, different types of clothing from that era, and fashion, and industry, and so forth. So tons of interesting data. In the last part of the talk, I just wanted to give you, kind of connect the dots back to the beginning when I talked about this idea of slow glass, how we can start using this to simulate a slow glass experience. And I wanted to start with an AR app that we built, which provides a slow glass experience where you can basically look through a window, essentially on the wall, into an antique scene. Hopefully the bass there wasn't too loud. Anyway, so you get the idea. You can basically peer through a window and it looks like you're looking at that scene from history. I'm not going to have time to go into many of the details, but the lead student on this, Shwen, has a poster this afternoon, so I encourage you to come to her session. She can tell you more about it. But I want to show you a few more results of stereographs and 3D visualizations that we can create. These effectively are light field renders from a stereo pair. And this is miners in a cave. This is one of the houses of the Senate or the House in the U.S. From century ago. Native Americans, so showing examples of events and places and people that are historically important. This is, I think, another Thomas Edison photo from his house. These are women on a boat going to meet their husbands after the war. This is, I believe, a car factory. I think it's forward. And just show you some failure cases. It doesn't always work. Sometimes it chops people's heads off. So this is Theodore Roosevelt's head being chopped off. And then if there are reflections and transparency, things like that can cause problems. Things that cause problems for stereo algorithms will cause problems for this method as well.
Steve, reminder, 3 minutes left.
Great. This is my last slide. So just to conclude, this is everything I showed you today is the work of my grad student, Xuan Liu. And she has a poster in the 1:30 session, so I encourage you to come to that. Here again is the website. If you want to take that down, if you're interested in the data, we should have that up shortly, and we'll send you email if you enter it at this website. Finally, I want to thank Rick Zalisky, obviously my co-authors as well, but Rick was the one who first mentioned slow glass to me, at a retreat many years ago, and so thanks to him. And that's it.